ah, 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 ah. My feet can't fall out of bed. I don't know how it goes, so I'm playing it instead with my symptoms of sorrow and dread. Said it'll come again and again. I love, I love, I love, I love, I love, I love. I love, I love. Why?
The frequency of collisions, and therefore the reaction proceeds a lot faster. In the case of concentration, if you increase the number of molecules of reactants, they can... Hello, everybody. Today, we're going to finish up chemical kinetics, and we're going to look at factors that affect the rate of a reaction. One factor that we already know that affects the rate of a chemical reaction is the concentration of its reactants. After all, that's what the rate law gives us. The rate law gives us the dependence of rate on the concentration of reactants.
Chat, chat, chat. Chat, 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 chat.
the second factor that influences how fast a reaction takes place is temperature. As you increase the temperature, the rate of reaction increases. And the general rule of thumb is for every 10 degrees centigrade increment in temperature, the rate of the reaction doubles. Now, the reason that the rate increases with temperature is because as you raise the temperature, the kinetic energy of the reactant molecules increase, and as the kinetic energy of the reactant molecules increase, they're going to move a lot faster, and the faster they move, the more frequent they can collide with each other. And the more frequent they can collide with each other, the rate of the reaction increases. Remember, when we looked at each elementary step in a reaction mechanism, we said that each elementary step requires molecules to collide with each other. And so the more frequently they collide with each other, the faster the reaction will take place. Okay? Now, both temperature and concentration affect how fast the reaction takes place because they're both affected by the frequency of collisions. If you raise either temperature or concentration, you increase the frequency of collisions, and therefore the reaction requires molecules to collide with each other. And so the more frequently they collide with each other, the faster the reaction.
I don't even. Just keep it. I'm never having those again.
These are good.
I had have a one. Yo, what are they even good for?
To wake you up.
Yep.
How do you just not react?
It's good.
It hurts, but it's good. That's insane.
Oh yeah. Wait. This is a field test. I'm actually falling asleep. Oh yeah. Oh yeah.
Oh, Mark didn't get to try it last time.
Hmm?
Mark didn't get to try it.
You to sleep.
Oh yeah.
Mark,
What's up?
do you want some gum? It helps you stay awake.
Nah, I'm lucky good. That looks like.
Yo,
That looks
Take
like
one.
Not gum, bro.
it is gum. It's Korean gum.
No, I'm scared
Yo,
of gum.
take one.
Nah,
This is Jacob's favorite.
what is that
I'm
gum,
literally
bro?
eating some right now.
He's
Nah,
eating
bro.
something right now.
Yo, trying to kill bait me, bro.
No, look at
What are you
me.
talking about? He has it in his mouth.
Nah. The way you approach me made it seem like it's like not normal, bro.
It is. It's normal gum.
Bruh, nah.
Just take a sniff. Take a sniff.
Nah.
Sniff it. Sniff it.
Nah, I'm good, bro. That's gonna die, bro.
I'm not gonna.
He heard it
I
through
knew
the.
it, I
He
knew
heard it through the door. I know he heard it through the door. He heard us talking about it through the door. I guess we just have to touch Mark while he's sleeping.
Yeah.
So glad he can't hear us right now, or else our plans would be ruined.
Take place. Hello, everybody. Today, we're going to finish up chemical kinetics, and we're going to look at factors that affect the rate of a reaction. One factor that we already know that affects the rate of a chemical reaction is the concentration of its reactants. After all, that's what the rate law gives us. The rate law gives us the dependence of rate on the concentration of the reactants. The second factor that influences how fast the reaction takes place is temperature. As you increase the temperature, the rate of reaction increases. And the general rule of thumb is for every 10 degrees centigrade increment in temperature, the rate of the reaction doubles. Now, Now, the reason that the rate increases with temperature is because as you raise the temperature, the kinetic energy of the reactant molecules increase. And as the kinetic energy of the reactant molecules increase, they're going to move a lot faster. And the faster they move, the more frequent they can collide with each other. And the more frequent they can collide with each other, the rate of the reaction increases. Remember, when we looked at each elementary step in a reaction mechanism, we said that each elementary step requires molecules to collide with each other. And so the more frequently they collide with each other, the faster the reaction will take place. Okay? Now, both temperature and concentration affect how fast the reaction takes place because they're both affected by the frequency of collisions. If you raise either temperature or concentration, you increase the frequency of collisions, and therefore the reaction proceeds a lot faster. In the case of concentration, if you increase the number of molecules of reactants, they can collide with each other more frequently, and therefore the frequency of the collision increases. And so we say one factor that influences how frequently the reaction takes place is the frequency of collisions, and the frequency of collisions is affected both by concentration and temperature. Now, it turns out, even though reactants factor, and therefore the frequency of the collision increases. And so we say one factor that influences how frequently the reaction takes place is the frequency of collisions, and the frequency of collisions is affected both by concentration and temperature. Now, it turns out, even concentration and temperature. Now, it turns out, even though reactants collide with each other and collide with each other frequently, they do not always lead to products, or they do not always increase the rate of the reaction. And the reason for that is that when molecules collide, not only must they collide with each other, and not only must they collide frequently, but they also have to have a minimum kinetic energy as they collide with each other. And unless they meet the minimum kinetic energy requirement, then that collision does not lead to products. So let's take an example of a reaction. So we're going to take a one-step mechanism shown here. This is a bimolecular reaction. So since this is a one-step mechanism, this is an elementary step, and you can see that when these two molecules collide with each other, they lead to products. And when these two molecules collide with each other, the kinetic energy of this collision is converted to potential energy that is used in breaking up bonds and forming new bonds. And so in this case, when these two molecules collide, if the kinetic energy of that collision doesn't meet a minimum requirement, then this collision will not lead to products and therefore will not increase the rate of reaction. Okay? And this minimum energy requirement is called the activation energy. All right? And the activation energy is given the symbol E subscript A. So if we want to understand activation energy, let's take a look at this graph, which is called an energy diagram. And on this energy diagram, the x-axis gives you the progress of the reaction, in other words, in time, and the y-axis gives you the free energy. And to begin with, if we take the free energy of the reactants and the free energy of the products, we can see that the free energy of the products is less than the free energy of the reactants. Therefore, the change in free energy for this reaction is negative. And so if delta G naught reaction is negative, we know that this is a spontaneous reaction, and therefore this will take place on its own without any external influence. However, when reactants convert to products, when the two molecules collide with each other, the minimum kinetic energy requirement is called the activation energy, and the activation energy is given here. So when two molecules collide with each other, if the kinetic energy of that collision does not exceed the activation barrier or the activation energy, then this will not lead to products. And so this shape here gives us the activation barrier, and the highest energy over here, shown here, is the activation energy, and the activation energy is always given in terms of kilojoules per mole. Lastly, in this diagram that we're looking at, the highest state is called the transition state. So the highest energy state in this curve is called the transition state. Now, if we take another example of a one-step mechanism, but this is a non-spontaneous reaction, then the energy diagram would look something like this. So let's take this example of M2 plus O2 giving you 2NO. Once again, this is a one-step mechanism, so it just has one elementary step, and this is a bimolecular reaction. Now, when we look at the energy diagram, we can see that this is the free energy of the reactants, this is the free energy of the products, and so when we look at delta G naught reaction, since the free energy of the products is greater than the free energy of the reactants, delta G for the reaction comes out to be positive, and therefore, this will be a non-spontaneous reaction. But now if we look at the energy barrier that needs to be overcome, this is what the activation energy would be, and the highest state energy is the transition state. Now we go back to this previous example of a spontaneous reaction and look at the energy diagram. We know that whenever we look at initial states and final states, that falls in the realm of thermodynamics. So when we predict 2NO, when the two molecules collide with each other, the minimum kinetic energy requirement is called the activation energy, and the activation energy is given here. So when two molecules collide with each other, if the kinetic energy of that collision does not exceed the activation barrier or the activation energy, then this will not lead to products. And so this shape here gives us the activation barrier, and the highest energy over here, shown here, is the activation energy, and the activation energy is always given in terms of kilojoules per mole. Lastly, in this diagram that we're looking at, the highest state is called the transition state. So the highest energy state in this curve is called the transition state. Now, if we take another example of a one-step mechanism, but this is a non-spontaneous reaction, then the energy diagram would look something like this. So let's take this example of M2 plus O2 giving you 2NO. Once again, this is a one-step mechanism, so it just has one elementary step, and this is a bimolecular reaction. Now, when we look at the energy diagram, we can see that this is the free energy of the reactants, this is the free energy of the products, and so when we look at delta G naught reaction, since the free energy of the products is greater than the free energy of the reactants, delta G for the reaction comes out to be positive, and therefore, this will be a non-spontaneous reaction, falls in the realm of thermodynamics. The realm of kinetics falls in the middle. How fast the reaction takes place will depend on the activation barrier or the activation energy. If the activated molecules collide frequently, and the more frequently they collide, the faster the reaction is. You can increase the frequency of the activation barrier, and to overcome the energy barrier, it turns structure for the reactant requirement to overcome the barrier. But nevertheless, if they come into contact with each other, when the point of turns in place, we can see effective product. EA.
Both know where it goes. There's a change. Everything stay the same. Always, ways. We don't know. I'll be the boyfriend in your wet dreams tonight. Roses on the skin, little virgin whales of wine. Okay.
Okay, what? What?
Or you're not?
They don't have the meal still.
Oh.
You still want like FM and McDonald's?
No, it's okay.
You want to order something to eat then? Oh, okay. Are you not hungry? But you've been snacking a lot.
I'm stressed.
Oh, that's what I do when I'm stressed. And copying me. Is that good?
What do you think?
Mm-hmm.
You don't like it. Why?
I don't want cold meat. I was supposed to take a nap when I came here, but no, I'm doing my homework. What are you looking at? Food? I'm gonna order food. Food? How much of this do you have left? One more bag? Chicken burger. What are you looking at? Can I see what you're looking at? I want you to. You really don't want to order food? Why? Had jokes I need to have over two on my left. You don't want to order food at all. It's 9 p.m.
I don't think you can order them on the app anymore.
Why?
Just recently.
You know, I figured out what alcohol tastes like.
Wow.
Tastes like the Samantha's rice milk tea at work apparently. Because it's like, it smells like alcohol, and then my coworker said, oh, it tastes like alcohol. And I was like, oh, this is what alcohol tastes like. It tastes like booty. Ow.
I'll put this back in the fridge.
Hey, got it. You don't want this.
Broke my laptop.
It's a ball and a matter I'm doing in the sky. In hell, there's heaven. Oh, 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 oh.
Because like I'm still learning your hair too, so like maybe in the future it'll be more of a like. Because I'm still learning your hair to be honest, so it's also like a learning process. You don't have to.
A, remember, is activation energy, and activation energy is always given in units of kilojoules per mole. R is the gas constant. Remember when we looked at gases and we looked at gas constants, there are two gas constants. One that is given in units of liters, atmospheres per Kelvin per mole, and the other is given in SI units, which is joules per Kelvin per mole. We want to keep everything in SI units, and so we're going to use 8.3145, which is the gas constant in joules per Kelvin per mole. But because the activation energy is always given in kilojoules per mole, we're going to convert joules per Kelvin per mole to kilojoules per Kelvin per mole, and so we're going to just divide it by 1,000. Okay, so the R value that we use in this equation is given in kilojoules per Kelvin per mole, which is the gas constant in SI units divided by 1,000. T, capital T, is the Kelvin temperature because we want to keep everything in SI units. We want to have it in Kelvin temperature. And lastly, A is a constant. This A here is a constant, and we call it the Arrhenius factor A. This constant is unique. Each
Do you guys have like a dark blue towel?
action
Lawrence,
has a unique
is
constant
very
value,
towel
and this
here?
Arrhenius
Before
factor
that,
A accounts for the collision
It's right
frequency
there.
and steric factor.
Oh,
Okay, so this is a mathematical equation.
the one on the
that makes
wall?
all the
Yeah, the dark
blue.
factors
Yeah.
That's yours?
of that
Yeah.
Okay, this
place.
is yeah.
Now, if you take this equation mathematically, if you take the natural log of k, this is ln k, and if you carry out an operation on this side, you will carry out the same operation on this side. So this will be ln a negative, the exponent will be negative EA over RT. So if you take the natural log on both sides, this is the end
red button on your.
and you rearrange this equation, what we end up with is all we're going to do is take this unit side, we're going to have ln k equals negative EA over R times 1 over t plus L. Remember, the slope action and the R from just, and our goal here is to do that. Okay? And if you want to know the derivation of how you go from here to here, your textbook gives you that derivation. And you can take a equation of SO2, CO2, and they give us the equation. Okay? Now they tell us the rate constant at 27 degrees Celsius is measured to be this time. So carry out the experiment in the lab, and at 27 degrees Celsius, this is the rate constant. And then now we just raise the temperature. When you raise the temperature to 77 degrees Celsius, the rate constant increases to this value. Okay? Now from these two measurements, we need to determine the activation barrier. Remember, activation barrier is what the activation energy for the reaction. All right? And in the second step, if you change the temperature to 17 degrees Celsius, you know what the rate constant can be. Okay, so let's start with part A. In part A, let's write down all the information that is provided to us. We are given T1, which is the initial temperature, which is 27 degrees Celsius. Remember, we have to keep everything in SI units, and keep everything as Kelvin temperature.
Oh, so these.
So
I
T1,
don't like these.
27 degrees Celsius was 273, which is 300 K. I know everybody doesn't want you to remind you that this is 373. And we know at T1, the rate constant is given to us, which is 1.22 times 10 to the negative 4. Now the second temperature, T2, is 77 degrees Celsius, so the Kelvin temperature will be 350 Kelvin, and this is
Hey,
T2,
Dad.
right? Remember, if we have two
Still.
temperatures and two rate constants, we can figure out what the activation energy is by using this equation. Okay, so we look at this equation, we know what K2 is, we know what K1 is, we know what T1 is, we know what T2 is, we know what R is, so we can figure out what the activation energy is. Alright, so the rest is just putting the values into this equation and making sure that systematically we're able to solve the math. Okay, so the next step is we're going to put the values into this equation. So I'm going to start by putting the value of K1 and K2 equals the activation energy divided by the gas constant. And because this activation energy is in kilojoules per mole, we need to make sure that this is in kilojoules as well. So we're going to take the gas constant and divide by
8.314.
okay, times 1 over
8.3145.
350, so this is T1, this is T2. Okay, the next step is I'm going to divide this number by this, and the result will be this. Okay? On this side, I'm going to say EA over this. Now I need to figure out the term for this. I'm going to multiply this by this. It'll be 350 minus 300. So this becomes this.
Wow.
The next step is I'm going to take this equation and we'll continue solving it. So if I take the natural log of this number,
Showing us how to do equations that I already know how to do.
energy divided by the gas constant. From this, multiply this from this, and divide by this, I end up with this number. And rearrange this, and I can figure out what the actual energy is. And the S comes out to 132 kilojoules.
Alexa,
So what I've done is
pause because Mark thinks I'm copying his music.
the root constants at 2 different temperatures. Now we're asked to figure out if you change the temperature to 17 degrees Celsius, now what is the value of the rate constant? So let's get it back. I'm going to say T1 is my initial temperature, which is 300 K, and I know the rate constant for that is 1.22 times 10 to the 4. Now T2 will be the value that I want to figure out, which is 17 plus 273, which is 290 K. We need to figure out what the rate constant is at this temperature. But in order to figure this out, I already know that the activation energy is 130 kilojoules per mole. So I can part 1. So I'm going to go back to this equation. And
Try that
see
gum.
once again, this is what we need to find. We know what K1 is, we know what T1 is, we know what T2 is, we know what the activation energy is, we know what R is. So we're going to put the values into this equation, and you can solve for it.
Okay, if you're not happy with it.
Yeah. I'm not gonna. Yeah.
Alright, is that everything?
Alright.
So
Wait, what gum are you guys
we
talking
should be
about?
able to also figure out
It's not caffeine,
the
it's
calculations
just
of
makes you
activation
up.
energy.
Like,
It's so strong,
what
bro.
do you mean?
You're
So up to this
eating
point, we
it.
looked at factors
Bro,
that
we had
influence
So
we-
what is it actually? Like, what is it actually?
Just done.
the
We're dead ass.
Look,
Dead ass,
look
dead
at what
ass.
it says. Look,
the relationship
no
between
sleep,
factors.
no drowsy.
Why would I want to wake up right now? It's so late.
Next,
Well,
we're gonna
it's,
look at
it's
No,
it's
it's not
not
caffeine.
It's just it wakes you up like.
Like
The
you
mint
feel
wakes
like
you up.
whoa, you feel like whoa.
Okay, who's chewing this?
Oh
right
no,
now?
last night we all tried it. Oliver had 3 at once.
It
was like, oh.
I feel like I'm being like.
No, I recorded Oliver last night. He was like, it can't be that bad. Take 3. Yeah. No reaction. Watch.
Yeah,
Record me. Record me.
There's look.
And he was like,
And I'll do another one,
ah.
maybe. Because I want to wake up too.
Will have its own activation energy or activation area. So if you want to
Why is smiling?
diagram for a 2-step, this is what it
Why is smiling?
X-axis is the reaction progress or time in seconds, and the y-axis gives you free energy, right? Now it turns out from thermodynamics, you know that this reaction
Why
is
recording?
spontaneous.
Why
And
recording?
so what that means is
Why
free
recording?
energy of products will be lower than free energy of reactants, and overall we look at delta G, the delta G for this reaction.
Why are you recording?
Okay?
Is it kicking in yet?
And so
Why are you
this-
recording?
the initial state and the
'Cause I wanna
final
see your
state
reaction.
looks at
Did all of them have a
Now, in
reaction?
kinetics, we want to look at how fast the reaction
Did
is.
all of them have a reaction? Let me see that
In the
reaction.
kinetic domain,
Here, it's on his
this
phone.
is the slow step. The first
Why are you
step is the
chewing?
slowest step.
Just chew it.
True.
The slowest step.
Break the black. Break the black.
Eat it already.
Open your mouth.
It's activation variance should be
Open
lower.
your mouth.
And
No,
because this is the slowest step,
No, is this like a? Nah, this is. I don't trust you guys.
I was doing
No.
all he did was
Just chew it.
And so this is the first step.
Bite it.
Reactants, temperature, products. And then in the second step, different from the second step.
Why are you recording though?
Cause taste it. Take a bite and see what happens.
No.
Why is he not eating?
Why is he not feeding it?
So the lesson in all this is that
Cause he's recording.
step one will have
Just
higher.
take a bite. It's strong.
Because it's also the slowest step.
Why are
step
you
one will
looking
have
at
the smaller
me?
rate constant between the two. And thirdly, because
Oh,
step
man.
one has the highest activation energy, it
It's
is
like,
the rate
like I'm barely taking a bite. It's really strong right now.
Yeah, exactly.
Oh my god. No, I'm not gonna fully bite this.
Fully bite it. He's chewing it.
Did I hear us yelling last night?
that corresponds to each individual
Did
step.
you hear us yelling last night?
Now the last thing we're
Wait,
gonna look at is we're looking at kinetics.
Oh my god, I'm breathing in like very cool. I haven't been it fully.
You want? Oh, wait, I think I have Oliver's reaction.
No, you have all our reactions from yesterday.
Oh yeah, you want to see?
Bro, I have barely bit this. Look at this, bro. It's really cooling my mouth.
You check the stream?
It was at the end.
Like, Indians.
It's supposed to wake you up.
I know how this would work. Actually,
And that actually woke me up.
I told you. Wow.
Oh my god.
Okay, can I fully bite
No,
it?
yeah, all. I think our reaction. All three.
This guy's gonna
For
cry.
the first time was better than all of it because he knew what he was expecting.
Look. Mark, come here. Look, that's us. Me biting it for the first time.
Bro.
And I was just passing it around because we didn't kick yet.
And when I was like, what is this? And then
Oh my.
I hate this,
I said,
bro.
whoa.
Oh my.
I don't think it is
Look,
for glasses.
look.
It's not bad. It's not bad. I don't know why you were recording, bro. It's just very limited.
This is my reaction.
Why are you screaming?
What did you see? I don't know what I'm doing. Wait, let me try. Hey, that shit light, bro. That shit light.
Keep breathing.
I'll never keep saying this shit light, this shit light.
This shit nothing in there. I'm gonna have.
Did you try this while I was cutting hair, bro?
I don't know what this is, but read. What's the box
It's supposed to make you wake up, and it did.
Yeah. Oh yeah. I'll have no. Is this not caffeine in it?
Yeah, for
No.
me?
I have no reaction. I'm scared. No reaction.
I thought it was gonna like.
No,
One more.
it's like not bad at the beginning. Then when you chew
I wanna try
longer,
one now.
it's like
One more.
Like, wait, who's this
Then
now?
breathe in after you.
Jacob's now.
Where'd you buy it, Jacob?
I still.
No, I bought it
I get why
at
it's
H Mart.
Like,
like
to
$2
wake you up.
Bro, I need that for glasses.
Yo,
And I have some in a Ziploc bag.
Oh.
I know. Yeah,
it's so strong.
Oh, it
Wait, give
kicks
me one,
on.
give me one. I want to try
Yeah,
one.
dude.
You want it?
Yeah, I like them.
What is
It really.
Breathe into your
I'll
mouth.
take some in a Ziploc bag.
Deep, like on deep.
so
No, it's gonna.
I still feel it, and I spit it out.
I'm gonna eat
I
I
mean,
literally, this is
it's-
what doctors do.
It's supposed to wake you up,
I know how this would work. Actually.
and that actually woke me up.
I told you.
Oh.
Wow.
Okay, what's up?
I still feel it. Oh my god.
Definitely.
This guy's gonna cry.
Mommy, please.
Okay, that's good.
I thought this was supposed to help you
this was
sleep.
safety. This was safety.
No, it's supposed to
When I'm
wake
sleepy,
up.
bro, oh, this is gonna help me. Where'd you buy this? How much?
Like $3.
Okay, mellowed out. I thought it was like.
Random Chinese website.
Why is it black?
How you guys like this, bro?
That's insane.
Oh,
yeah, really.
Oh my, I'm sweating.
Ow.
Oh my god.
that's all in my nose.
You're still chewing it?
I
I
actually love this
spat
so
mine
much.
out.
Just, I'm gonna go get some more, bro.
So we're at the checkout aisle. Like, we're eating out.
And H Mart?
Yeah. Like, when it's at the register.
Oh,
No, I'm gonna get H Mart.
I'll do that after we
Look at this one.
I think drinking water is gonna go worse, so don't drink.
My kicks.
whatever you
It's
say.
gonna hurt.
I get why it wakes you up now. I didn't buy my Uber yet.
Hey, that mellowed it out.
Oh, okay.
Oh, that's minty. That's fresh.
Let me get the aluminum foil. Let's keep it next to me. Oh, I don't want to take that tote back home.
I literally Google translated that at the checkout because there's no sticker that translates it. And it said sleep gum.
Yeah, no, it's a drowsy
It's like
gum.
really nice honey.
And then
It
you
has, like,
told me
honeycomb.
it's to wake you up.
No, I said it's either it's a 50-50 chance it wakes you up or goes takes you to sleep.
Wait and see. I'm gonna
Reset it don't work.
off if the
Huh?
2 minutes away. Go do this one.
It's sugar-free too with Xylitol. Xylitol.
No.
Use my car. Yes. Oh my god, I sweat so hard when I was using it. Like,
Oh, I got a little bit of a kick.
yours?
Is it still in your mouth? It would be, yeah.
I spit mine out and I still.
Like it has to be
Rico. Does it say sweet or sweat?
I saw this. I thought it meant don't take it while in the car.
Yeah, I would not take that in the car. It starts going down.
Oh.
May I have my...
I saw this. I thought it was for sleep.
No, you remember you Google Translate at H-Mart?
Yeah, it said sleep.
No, you just
Sleep
told me,
gum.
oh, this helps you not sleep.
No, I said it helps you sleep.
Well, I heard it helps you not sleep.
Oh. That was strong.
He gave it to my brother. This will have his ear. I already know.
Okay, here.
Oh man.
I think you should do it. Okay, it doesn't do her, you know what you do.
I don't want to do it. Oh, love it. No.
Is there a game today?
No, those are color guard stuff.
Oh.
Bruh.
He's always on my For You page. Damn.
Did the dog get it?
Yeah, I think so. This is gonna be your dog when it gets into your packages.
That's funny. Huh? I don't get it.
Oh, nothing. I'm just showing you her feed.
What's that?
Skewers.
Oh.
They're skewers. You know how expensive skewers are? Oh, they're fire alarm.
Are you using the mic?
Huh?
Are you using the mic?
No, you want to use it?
Nah. Thanks.
To charge it?
Yeah. Burp.
Why you bark?
Some guy's calling someone on the phone.
Get after their number. Then prank call them.
Oh my gosh. If she actually isn't a company.
What if she's like working her 9 to 5 right now?
She said latest 10.
10 today?
Yeah.
I think you got ghosted. Wait, pick up 10 today?
She said latest 10
AM?
p.m.
Today?
Yeah.
Oh yeah, that's long gone. You already give her the address and everything?
Mm-hmm. Not the address, I gave her in and out.
Huh?
The in and out by right there.
Oh.
What if she's driving? That's why she can't answer you.
Da-da-da.
doing?
I'm tweaking out. I hate doing homework. I'm like, this is what Oliver feels like.
Don't say that sentence again.
Okay.
Don't do that. Ew. I'm mad at you now. I'm mad at you. Don't touch me. I said don't touch me. I said don't touch me. I said don't touch me.
Oh, say, don't touch me.
Don't touch me.
Hmm?
I said don't touch me.
Really?
Yes.
Really?
Stop.
Why?
I said so.
Okay.
Do pregnant women have matcha?
I don't know.
Do pregnant women have tea? Because a lot of people come to my job and buy tea. And they're all pregnant. A lot of people work at my job.
No circumstance. Above.
Licorice. You're saying if someone's pregnant, they can't have licorice?
Licorice sucks anyways. No one's gonna have licorice
I like
anyways.
licorice.
Oh, that's not.
I like all the old people candy.
Why?
No, I like it. It tastes good. I like Micah Nights and I like Dots. They're like
Why?
my favorite. Like I also like those okay, it's not like I like them, but like if I see them I will want them. Like, you know the granny strawberry candy that you can buy a bulk?
Like
The one
bonbons?
Huh?
Bonbons?
Bonbon. No. It's like
Yeah, strawberry bonbons. These?
yeah, I like those.
Everyone likes those.
Oh, man. You only can get them if the grandma gives it to you. No, I know only can have it. I'm gonna eat it. Why is that? Why?
Make sure to grab your chicken nuggets and Malona.
Don't want to make another trip back to you. You know Chiba's birthday today?
Yeah.
Now you know.
Oi, oi, oi. Back up.
Oh, I'm gonna crash out, bro. This always fucking happens.
Why?
You asked hell shit about the iPad. And now they're not gonna reply. Insane.
Must be overstuffed with the food in the app.
I showed something like that to you.
I know. I tried showing it to you.
You already finished it?
No.
Did you?
No. I was doom scrolling. And then I was eating at the same time.
Oh. I don't even need to stay for this. What?
Bro, you guys ran into Ireland. Bro, where's the fuck? Oh my gosh. She's gonna actually PMO. What?
Hi, and welcome back. In the previous lessons, we motivated and defined the notion of limit. In this lesson, we will give a set of rules to calculate some of them. These rules will be called the limit laws, and we start by stating them as a theorem. So let L and M be two real numbers, and we assume that the limit as x approaches c of the function f of x, and the limit
What do you need that much money for, bro?
as x approaches c of the function g of x exist, and
What's the
in fact we know their
gen
value,
meeting for
and they are going to be
Tuesday?
simply L and M. So the limit as x approaches c of
For
the function
Puso.
f of x is equal to L.
On the side, oh, it's like some fans. It's our last meeting.
Huh?
Bro, I'm
Like-
wasting my time waiting for this match.
Waiting for what?
Good girl.
Oh. Oh, to show your stuff?
Yes, bro, I'm trying to sleep.
Just tell her, if you're not gonna pick it up for the next hour.
And
I'm not
the
gonna
limit as x approaches c,
tell you. You really
the
want to sell
function
it?
g of x
You want to sell it
is
more than she wants to
equal
buy it?
to m.
What's
Then
it? You want it more than her?
the limit laws allow us to conclude
Just say, hey, are there any updates of you picking it up? If not, that's completely fine. I just need.
She's just not replying.
Then just say, sorry, I'm not gonna sell it to you right now. I have to go to sleep.
Okay. I'm so hungry too.
This Gen meeting is kind of not applicable.
Huh? Why? Tuesday?
Collect new memories and reflect on past ones during the last Omicron class intern hosted meeting.
Let me see this.
Dr. White Room 5 to 7. After events, gelatissimo and photo booth next to UCI. I have to though. This is what I have to walk in for. Is clubs. I gotta look for clubs.
If you don't make friends now, you won't.
Clothes?
No clubs.
Oh, clubs.
Just like
My days, my days.
Wait, where is it? Week 3?
These type of people. bruh.
Omi side out. Wait, what?
These clothes. Why is this hard to open now?
yeah, right. What happened?
Oh my days. I'm tired. I have class tomorrow. Come on, mate. Come on, mate. Don't do me like this, mate. If you're not gonna make it, just tell me. If you don't want it anymore, tell me.
Omni. Wait, what is the Gen meeting?
Just like how do I explain it? They're like putting stuff in past meetings, like memories or whatever. It's from the intern class. Like all the interns this year are hosting it.
They can't be doing that for 2 hours.
True.
Yeah. I feel like that's just a main event. And the Minecraft thing was fun.
I'm still gonna go. I mean,
You thought it was for girls only.
I did. I don't know. Who's so girls, bro? Like, what is that supposed to mean?
Bro thought it was girls only, bro. Segregated club. You thought the club was segregated by gender.
Yes, I did.
That's insane. No way. No way.
If I saw Puso girl, if I saw Puso girl slow, I'd probably think that.
I'll taste it.
the following. First, we write the sum law. We're interested in evaluating or determining the existence of limits of more complicated expressions in terms of f and g. The simplest one is to take the sum. So the limit as x approaches c of the expression f of x plus g of x is what we're looking at. And the limit laws simply state that if I know that the limit of f of x and the limit of g of x exist, then the limit of f of x plus g of x also exists. Not only do I know it exists, I can also calculate it as the limit as follows. So again, the limit of f of x plus g of x. And now the limit laws tell us this is equal to the limit as x approaches c of f of x plus the limit as x approaches c of g of x. Or, since we know their values, simply L plus m. Colloquially speaking, we could simply say this as the limit of the sum, which is this thing, is equal to the sum of the limits. Now, the limit laws tell us this provided that the individual limits exist. Otherwise, the limit laws simply don't apply, and we can't use them to conclude. This is the first example of a limit law. The others will be similar and based on different ways of combining these functions f and g. In fact, the second one that I'm going to be writing is really just the simple variation of the first, and therefore I'm not going to write it separately, but I'm going to indicate how it works by simply stating that instead of looking at the sum of two functions, we're going to consider the difference. This gives us the difference law. And all I need to do is change the plus into a minus. And I'm looking at the limit of the difference. And the limit laws simply say that that limit exists and can be calculated as the difference of the limits, or L minus m. So this gives us a second law that's very similar to the first law. The third law, which is going to be called the constant multiple law, as the name says, involves a constant. So I'm going to first define that constant, so let's say as k. Then, again, first we say that something exists, and what exists? Well, the limit as x approaches c of the function k times f of x. So this
You're actually
limit
such a
exists,
tsundere, bro.
and I can calculate it
You would never have
by
it again.
simply pulling the k out front. So the limit of k times f of x is equal to k times the limit as x approaches c of f of x, or k times L. This is the constant. The next one's going to be the product law.
You know what
Another
I
way of
hate
combining.
and would always skip?
Huh.
Those Halloween ads, bro.
What?
Any Halloween ads, like, I was skipping that shit. I didn't even want to hear it.
What?
Cause like,
$5
What's
mask
Halloween
that's
ad?
too
scary.
Too
Like, you know when
scary.
it's near Halloween, there's like hecka like scary ads.
No.
Really?
Wait,
I don't get those.
You actually get scared of them?
I actually just get them. Like even when I'm showering, like I turn that shit down way too fast.
Wait, like
When they're screaming or like you can just tell it's like a Halloween ad, I turn that shit down. When I used to
I
watch
guess
YouTube
so.
and shit,
Oh yeah.
it might just
Watch
be me.
YouTube in the shower?
No, I used to play music from YouTube in the shower.
Defining f and g. So the product law then states that the limit as x approaches c of f of x times g of x is equal to the limit as x approaches c of f of x times the limit as x approaches c of g of x, or simply L times m. I could again write this colloquially as the limit of the product is equal to the product of the limits, provided that the individual limits exist. The next one, well, you can guess, we've done sum, difference, product. The next one is going to be the quotient law. I don't want to just introduce that in here as a red because there's an additional wrinkle that we need to address. When you're multiplying, it does not matter what values L and M are, but you know for sure that I cannot divide by 0, so if I want to have L over M as my final answer, I need to assume that M is not equal to 0. And then the limit as x approaches c of f of x over g of x. exists. And the limit as x approaches c of f of x over g of x is equal to the quotient of the limit as x approaches c of f of x over the limit as x approaches c of g of x, or once again, L over m. And this is, of course, again, why we need that m is not equal to 0. So now we get two more laws. And those have to do with powers and roots. So to do that, we let n be a positive integer. And this is going to happen for both E and F. So law E is going to be called the power law. And it simply restates essentially the same idea, but for power expressions. So the limit as x approaches c of f of x to the nth power exists. And I can rewrite that limit as the nth power of the limit, or L to the n. Now, we will do the same thing again for roots. But as above, we already saw that when you're dividing, you got to make some extra assumptions. And the same thing is when I'm using a root, particularly when it's a square root or in general an even root, I cannot evaluate this for all real numbers. I, for instance, can only evaluate square roots, at least as a real number, for positive or non-negative inputs. So we will have to be careful here when we come up with the root law. So first of all, again, we will write and that this limit is equal to the nth root of the limit as x approaches c of f of x, or simply the nth root of L. Now, as I just said, we need to be careful that we are not evaluating something that is not a real number. Our limits here are supposed to be real numbers. Or that we're not trying to give a value to a limit where I am not able to evaluate the expressions as real numbers. So this leads to the following statement: provided that if n is even, then either L is greater than 0. If L is greater than 0, there's no problem. Also, by the way, if n is odd, there is no problem, because the cube root or fifth root or any other odd root can be evaluated as a real number for both positive and negative numbers. Now, if n is even and L is 0, then we need to make the further assumption that f of x is greater or equal to 0 near x equal to c. And as before in the definition, we do not care one bit what happens at x equal to c itself. So these are the laws. We have the sum law, the difference law, constant multiple law, product law, quotient law, power law, and root law. So this is a lot of machinery that will allow us to compute limits. This is a theorem. We do need to have a proof before we can really rely on it. But we choose to not prove these limit laws here. The reason is the theory of limits evolved over a period of several hundred years after the discovery of calculus. The reason was that a clear, precise, quantitative definition of limit is very subtle and to some extent anti-intuitive. And that's also the reason why it is really not advisable in the first introduction to calculus to delve too deeply into limit theory. Nonetheless, in the book, in section 2.9, example 1, let f of x equal to x cubed plus 5x, and, if possible, find the limit as x approaches 2 of f of x. Now, the point, of course, is that this is going to work and that we can use the limit laws to evaluate this limit. So let's start. Limit as x approaches 2 of f of x. First, we're going to simply write what f of x is to see what this gives us. X cubed plus 5x. Now, to evaluate the limit of the expression x cubed plus 5x, and using the limit laws basically means that we need to look for what limit law might be applicable. Really, in the end, this is first and foremost the sum of two simpler expressions, namely the expression x cubed and 5x. So therefore, really, we can use the sum rule to break this down. So using the sum rule, we're going to write this as the limit as x approaches 2 of x cubed plus the limit as x approaches 2 of 5x. So the limit of the sum is equal to the sum of the limits. Now, we will have to revisit this later because, as we made the point above, there is a proviso, x cubed. Same over here. This is 5 times x, which is really an instance of the constant multiple. rule or law. So I can rewrite this as limit as x approaches 2 of x to the third power plus 5 times the limit as x approaches 2 of x. And now from the last lesson, you might remember that this is a limit that we know how to evaluate. Numerical value 18. So 18 is our final answer. That's the limit of this expression. Now, we have a number, we have an answer, but we want to make sure that this is actually correct. And that means we need to justify the use of the limit laws. Remember,
It's
the
the
limit
athletes.
laws apply
They're-
only
In one of the
in the
classics,
case
two
that
of the
the
classics got hit
individual
by them
limits
too.
exist. So if I want to use the sum law, I need to make and ensure that this limit exists to be
cookie into our room last night probably meant it for it to be the other room.
Probably.
able to say that this limit exists and is equal to this.
I was about to say.
That means I need to simply verify that the sum, where actually what condition for the rightly over the expression x.
I took a picture of his. Totally caked up. It's like a hazard. I'm gonna eat my Chipotle. I want to talk to Ivan more. Glad I ran into him. I saw a guy pressing 95 dumbbells on the bench, bro. Insane.
X minus 5. And we're interested in the following limit. As x approaches 3 of f of x.
Should I hit chest tomorrow?
Again, we should say if possible, because there's not always a guarantee that a limit exists, even if we say fine. Now here in this case, we will see this limit exists. So let's proceed as before. Limit as x approaches 3 of f of x is equal to the limit as x approaches 3 of the expression x times x minus 5. Now we deconstruct the given function. So first and foremost, it's a quotient. So we apply the quotient law. So we write this as a quotient of limits. In the numerator, the limit as x approaches 3 of the expression radical x plus 1. And in the denominator, the limit as x approaches 3 of the product x times x minus 5. And you might be able to see how we're going to continue. This is a radical expression or a root expression, so we're going to apply the root law. This is a product, so we're going to apply the product law. Furthermore, inside we have an application expression, the square root of the limit as x approaches 3 of x plus the limit as x approaches 3 of 1 over the limit as x approaches 3 of x times, and then here we have a difference, so this will be the limit as x approaches 3 of x minus the limit as x approaches 3 of 5. Now we can evaluate each and every one of these limits because they are now in the form where we have a theorem that tells us how to evaluate them. And we shall see that this is then simply the square root of 3 plus 1 over 3 times 3 minus 5. That's the square root of 4 over 3 times minus 2, and that in turn is 2 over minus 6, or minus 1/3. Again, we need to justify the steps, and that can be seen follows from the same reason as before. This limit exists, therefore this limit of the difference exists, this limit exists, therefore the limit of the product exists, and so on. And you can again see that this watching.
Forgot about the binomial theorem.
Remember what this was? That's this triangle.
Oh, I remember that shit. It's so stupid, right? You literally don't. I haven't used it once after math 2A. Yeah. Oh, my legs are so small, bro. My body would be it's like, yeah, they're using your body for I got the mic connector. I'm the winner.
You do.
Oh, that's what I was gonna watch. You guys watch K-dramas? You watch K-dramas, Mark? Classic. Classic Mark. Classic Mark moment. I'll watch one episode of this and start doing my physics. Oh, why is this show so edgy? she's dead.
Hello and welcome back. In today's lesson, we will discuss the concept of a continuous function. Functions are one of the key mathematical ideas that help us model nature. Most, but not all, natural phenomena are continuous. Usually, the average is global warming, no one expects the average temperature of the Earth tomorrow to jump by 275 degrees Celsius. Thus, to model continuous phenomena, we need continuous functions. Intuitively, a continuous function is one whose values don't suddenly jump. That is, if x is near to z, then f of x is near to f of z. We also think of a continuous function as one whose graph is unbroken. In mathematics, for such intuitive concepts as continuous, broken, and unbroken to be meaningful and useful, they must be made quantitative or provable. And the task of doing this is often quite challenging, if not daunting. In the 18th century, right after the birth of calculus, the concept of function was this. A function is simply a formula given by an algebraic or trigonometric expression, as for example the formula, say, f of x equal to sine of 3x plus 17 over 2x to the fourth plus 5. As the function concept expanded to include ever more cases needed in applications, there was an increasing need to give a rigorous definition of what continuity actually meant. The first step towards a mathematical definition of continuity was taken by the 19th century mathematician Bernhard Bolzano and then completed at the end of the 19th century by the German genius Karl Weierstrass. Initially, this definition, which is based on limits, may seem weird to you. It may also seem to have no obvious relation to the intuitive idea of unbroken graph. But rest assured, Weierstrass got it right. So let's begin with the definition of continuity of a function f of x at a point x equal to c. Assume that f of x is defined on an open interval containing x equal to c. Then f is continuous at x equal to c if the limit as x approaches c of f of x is equal to f of c. If the limit does not exist, or if it exists but is not equal to f of c, we say that f has a discontinuity or is discontinuous at x equal to c. Before we give you examples of this definition in action, let's extend it to an interval. So here's our second definition. Continuity on an interval. A function f of x is continuous on an open interval, provided that it is continuous at every point x equal to c in the interval. And then similarly, a function f of x is continuous on a closed or half-open interval if the appropriate one-sided limits at the endpoints exist and equal the function values at these points. Again, a point x equal to c, where a function f of x is not continuous, is called a point of discontinuity. And in the 18th century, when functions were given by formulas, points of discontinuity were really just for the most part points where the algebraic or trigonometric expressions could not, in some sense, be naturally defined, as for example for the functions tangent x or secant x at x equal to pi over 2. Let us consider another example. And here we go. Determine whether the function f of x equal to 1 over x squared minus 4 is continuous at x equal to 1 and at x equal to 2. This is a rational function, which is of course a quotient of polynomials, and you can see that it is not defined at x equal to 2 or x equal to minus 2 because, well, at these points we would simply be dividing 1 by 0. Now, let's consider the graph to investigate this function a little bit more. Now, the methods allowing us to accurately picture such a graph will be discussed in Chapter 4, but for the moment, let us use our pre-calculus knowledge and accept this picture as being correct. First, let's investigate whether f of x is continuous at x equal to 1. Now, based on our limit definition, what we need to check is whether the limit as x approaches 1 of f of x is equal to the value of the function at x equal to 1. This is also now where the value of the function plays a crucial role as this concept is being discussed. Before, when discussing the value of the limit, we could ignore the function value at the point that we're approaching. But now this is an integral part of whether this is actually continuous at x equal to 1 or not. It is more than having a limit. It is having a limit that then is equal to the function value. Now, let's calculate f of 1. Well, f of 1 is 1 over 1 minus 4, and therefore minus 1/3. Now, what is the limit as x approaches 1 of the expression 1 over x squared minus 4? Now, we saw using the limit laws that we can write the limit of the quotient as the quotient of the limits, and the limit of the difference as the difference of the limits, and the limit of the square as the square of the limits, as long as any and all of those limits existed. And when it's a quotient, the denominator didn't turn into 0, which it won't. As x approaches 1, in the end, we're simply just retracing the same steps as when we calculated this. And we can see that the limit is equal to the function value. So therefore, f of x is continuous at x equal to 1. Let us check this result against our intuition of the curve being unbroken where the function is continuous. Here is x equal to 1. The function value is approximately minus 1/3, and it sure appears as if the curve that represents the graph of f of x is unbroken at x equal to 1. Now let's investigate what happens at x equal to 2. Again, the question we need to ask is the limit as x approaches 2 of f of x equal to f of 2. Now, the limit as x approaches 2 from the right, as we have seen in previous examples, and we can also see from the graph, is infinity. Because here, as x approaches 2, f of x becomes arbitrarily large. And similarly, the limit as x approaches 2 from the left of f of x is minus infinity. F of x becomes arbitrarily large, negative, as x approaches 2 from the left. Furthermore, f of 2 is undefined. F of 2 is undefined. And that, of course, immediately prevents f from being continuous at x equal to 2. But even if we were to define f of x at x equal to 2, say 0, and made it continuous there. Let's see how this works with an example. And here we go. If possible, extend the function f of x Given by square root of x plus 1 minus 1 divided by x to a new function f twiddle of x, so that f twiddle of x is continuous at x equal to 0. Let us consider the graph of function f twiddle of x, so that f twiddle situation continuous at x equal to zero. let us consider the graph of f of x to help us in our understanding of the situation. So here is the graph of y equal to f of x. It is defined for values of x greater or equal to -1. And that is simply so that the radicand, which is the thing under the radical, is non-negative, so that this becomes a real number. Everything else is okay, except when x is equal to 0. Since we would be dividing by 0, f of x is not defined at x equal to 0, and therefore there is no point on the graph with x coordinate 0. On the other hand, the graph that we're sketching here seems to indicate that the curve simply has a hole at x equal to 0. That is the idea behind trying to do something to make this function continuous. In some sense, to try to unbreak the graph at this point, x equal to 0. Now, to be able to do that, we need to know what the limit is at x equal to 0, as x approaches 0. So let's do that. We're trying to calculate the limit as x approaches 0 of f of x. Or, since f of x is this expression, the limit as x approaches 0 of the expression radical x plus 1 minus 1 over x. As you have seen in previous examples, the trick here is to expand this by the conjugate. So we're going to multiply both numerator and denominator by the conjugate of the expression, and that is radical x plus 1 plus 1. And then we see what we get. Now, firstly, we end up with the limit as x approaches 0 of the difference of squares in the numerator. And the square of the square root of x plus 1 is simply x plus 1. And then minus 1 over x times the square root of x plus 1 plus 1. And then we can simplify. We get the limit as x approaches 0. X plus 1 minus 1 is simply x. And we still divide by x times the square root of x plus 1 plus 1. And now we can cancel these x's. And we're left with the limit as x approaches 0 of 1 over the square root of x plus 1 plus 1. And now from the last section, you know that we can apply the limit laws. The denominator does not go to 0 anymore, and then we can apply the appropriate limit laws, and after a few steps, we will find that the limit is 1/2. And if you wanted to go through the steps, you would first evaluate this limit, and that is going to be the square root of the limit of x as x approaches 0 plus 1, which then goes to 1. The square root of 1 then becomes 1. 1 plus 1 is 2. 1 over 2 is 1/2. So the limit as x approaches 0 of f of x is indeed 1/2, as was suggested by the graph. It is a reason to expand by the conjugate this function on the half-closed half open interval from -1 to infinity. And this ability to extend f to a continuous function f twiddle can be described by saying that f of x has a removable discontinuity at x equal to 0. That are prima facie meaningless lies at the very heart of the beginnings of calculus.